In graph theory, if G is a connected graph, its edge connectivity, denoted as lambda of G, is the minimum number of edges that would need to be removed in order to disconnect G. So I have three examples of graphs right here. Let's take a look at each one and determine the edge connectivity of each graph. So if we consider this first graph right here, this graph has 6 total vertices, and it's currently a connected graph because it's possible to go from any vertex in the graph to any other vertex just by traveling along edges. Now consider if we removed this edge right here from the graph. If we removed this edge, this would still be a connected graph because we can still get from any vertex to any other vertex. But now imagine if we removed this edge as well. Well, now all of a sudden this graph is disconnected because there's no way to go from any of these vertices to any of these vertices via edges. So for that particular case, if we removed those two edges, we created a disconnected graph. But now let's consider our original graph again. If we instead just removed this edge, well, that also produces a disconnected graph where there's no way to go from these vertices to these vertices by traveling along edges. So in that case, we only had to delete one edge to make this a disconnected graph. So that would be the minimum number of edges that we had to delete to make a disconnected graph. So we would say that the edge connectivity, or the lambda of G, as we denote it in graph theory, of this graph is just 1. We only have to delete one edge to produce a disconnected graph. All right, now let's check out this second graph right here. This graph has 5 vertices, and currently it is a connected graph because we can travel from any vertex to any other vertex just by traveling along the edges. So what would be the minimum number of edges that we would need to remove to actually disconnect this graph? Well, if we just go through every single edge and we say, if we deleted this edge, would this create a disconnected graph? We can see that no, this would still be a connected graph. We can still go from any vertex to any other vertex. Now instead, what if we deleted this edge? Well, in that case, we can still see this is still a connected graph. So it turns out for this particular graph, we have to remove at least 2 edges. So for example, we would need to remove these 2 edges to produce a disconnected graph. So if we removed those edges, we can see that it would produce a disconnected graph with 2 components. So there's no way to go from these 2 vertices to these 3 vertices. There's no edge that allows us to do that. So for this one, we would say that the edge connectivity is 2. So in other words, the minimum number of edges that we would have to remove from this graph to disconnect it is 2. And by the way, we could have also removed these 2 edges as well to produce a disconnected graph. So often there are multiple sets of edges that you could remove to produce a disconnected graph. But we'll find that the minimum number of edges that we have to remove to disconnect this graph is 2. All right, now let's consider this last graph right here. This graph has 5 vertices, and it's currently a connected graph, so we can go from any vertex to any other vertex just by traveling over a sequence of edges. Now for this graph, we'll notice that if we try to remove one of the edges, there is no edge that we could remove that would produce a disconnected graph. But if we remove this edge and let's say this edge right here, by removing those 2 edges, we could produce a disconnected graph, which has 2 components. So there's no way to go from these 2 vertices to these other 3 vertices just by traveling along a sequence of edges. So for this graph, the edge connectivity, or the minimum number of edges that we have to remove to disconnect the graph, is 2. So those were just a few different examples of how to find the edge connectivity of a graph. Now before wrapping up this video, one question you might have is, what is the point of finding the edge connectivity of a graph? Well, when we're applying graph theory to real-world situations, edge connectivity is a way to measure the robustness of a graph. So if you imagine that, let's consider this graph 1 right here. Imagine that each of these vertices are buildings, and imagine that each of the edges are power lines that are connecting the buildings. When we say that this graph has an edge connectivity of 1, we mean that only one of these edges, or in this case, only one of these power lines would need to fail to disconnect the buildings. Or if you instead imagine that these vertices are cities and the edges are roads between the cities, we would say only one road has to fail or flood or something happen to it to disconnect the cities from each other. So edge connectivity is just a way to measure how robust or how resilient a network or a grid or anything else that can be modeled by a graph, how robust it is to failure. Or in other words, how many connections would need to fail to actually disconnect the network. So that's why edge connectivity is actually useful in the real world.